Our application programming interface, or API, is designed with a great deal of care. Its construction follows a set of core principles. First, we aim for strong coherence between the mental model and the API itself. The mental model is the term we use to describe the way you think about a digitizer and its many functions. The API is what you, as a programmer, use to operate a digitizer in practice. Second, since a digitizer is a ubiquitous device used in a wide variety of domains, there is an inherent challenge in providing an API that matches your expectations, as a user focusing on just one of the many application areas. We strive towards providing an experience that is as smooth as possible for the largest group of users. Third, while our digitizers are packed with a large number of features, the majority of them are optional. They can be used to great effect, to make the system design simpler, or to greatly improve performance if certain assumptions hold true. Regardless of whether you're acquiring a few samples each time you press a button, or if you're using the digitizer to control a complex system and streaming data to a GPU at 15 GB per second, the mechanisms you encounter should feel logical and fit together as a whole. If the digitizer's mechanisms are easy to explain, they should be easy to understand. Fourth, maintainability. The way we design the interface should stand the test of time, as simple as that. Let's delve a bit deeper to highlight a few important principles. The digitizer is composed of many functional blocks. These are organized in a hierarchy that forms the backbone of the mental model. You will encounter this hierarchy in many places, as the table of contents in the digitizer's user guide, and also as the structure of the API's parameter tree. In this way, we use the programming interface to propagate the mental model. Modern editor features can be leveraged to simplify the programming task. You don't need to commit as many arcane details to memory if parameter navigation and feature discovery is handled by your editor's autocomplete. Fewer error handling sites make the control flow easier to read and reason about. For that reason, we believe that fewer API calls processing larger sets of data is preferable to many API calls processing small amounts of data. Applying configuration parameters is a commutative operation. It doesn't matter if parameter B is set before parameter A or vice versa. The resulting behavior is the same. When validating parameter values, we prefer clear error messages and involving the user in correcting any invalid values, rather than performing silent adjustments behind the scenes. What you set should be what you get. With sane default values for the digitizer's many parameters, you only need to modify a few of them before data can be acquired. Our foundation is a C API consisting of a header file and platform-specific shared library files for dynamic linking. This foundation enables you to create extensions for other programming languages that feature a C foreign function interface. One such extension we provide in our SDK targets the Python language. In the form of the PyADQ package, we deliver first-class support for operating our digitizers from Python. Applications interfacing with our digitizers normally follow a control flow that looks like this. In the identification phase, you query the host system for a list of all digitizers. From this list, you select the ones you want to interface with. Usually, this includes all of the digitizers, but you're free to choose a subset. In the initialization phase, you set up the digitizer's clock system, potentially choosing a specific sampling frequency and/or from where to source the reference clock. Synchronizing multiple digitizers in a single system usually involves some choices in this step. By default, the clock system is set to use its internal clock reference and to target the highest sampling frequency possible. In the configuration phase, you apply the parameter values that will determine the behavior of the digitizer in the upcoming acquisition phase. In the acquisition phase, the digitizer is actively listening for the trigger conditions specified by its configuration. Each time the trigger condition is fulfilled for a channel, the digitizer acquires a record, a contiguous set of samples from that channel. These records are continuously transferred to the target endpoint, which is usually the host computer's RAM, but transferring the data straight to a GPU is also common. The digitizer will remain in this phase until the user stops the acquisition. In the cleanup phase, you perform a controlled shutdown of the digitizer and return system resources to the host operating system. At any point in the flow, the previous phases can be revisited. However, returning to the same phase can only be done in one direction. For example, if the digitizer is reinitialized, which disrupts the clock system, its configuration is lost and you'll need to reapply the parameter values.